Good day to all. I hope you're all having a good day. Today we will be beginning with the first lesson of the A-level physics syllabus, and that is physical quantities and SI base units. So firstly, let's learn how to distinguish a physical quantity from other quantities. So what is a physical quantity? A physical quantity is one that can be measured or calculated, i.e. they have a value and a unit. So for example, let's say I draw this line. This line, after measuring with perhaps a scale, you can say that it's 13 centimeters. Now don't actually try and measure this because it's an approximate value. I'm not sure whether this is 13 centimeters or not. And this 13 is the value, and centimeters is the unit. And the other way is through calculation using a formula. The two ways to define physical quantity. The first one is word definition. Let's just write it as word definition. WD for word definition. And the second one is by equation, by defining the equation. Word definition, for example, let's say speed. What is the formula for speed? Speed is equal to distance by time. To define it in terms of words, you say that speed is defined as the rate of change of distance. So distance divided by time, so rate of change of distance. The distance covered in whatever time. And defining the equation is just like stating the equation. So let's say speed is equal to distance by time. So speed is equal to distance by time. Okay. Now, there are 7 base quantities, and these are like, so there's derived quantities and base quantities. Derived quantities can be derived into simpler quantities, and those simple quantities are base quantities. And there are 7 base quantities. The first, and these are the 7. The first one being length. And we give length the symbol L. Pardon that. And its unit is meters. The second base quantity is mass. Okay, I'm just gonna write the symbols because it's a bit hard for me to write using a mouse. So the first derived quantity, the first base quantity is L, which is length, and its units is meters. The second one is mass, and the unit of mass is kg. You may be all familiar with this. Third one is time. Now the base quantity, this unit is seconds. Electric current, we give the symbol I. Quantity and symbol is, sorry, not the symbol, the unit is amperes, A. The next one is temperature. We give this either theta or T. And the unit is, the base unit is Kelvin, not degrees Celsius, not Fahrenheit. Maybe a surprise to a few. The next one is amount of substance, mole. We give this the unit mole. And the last one is almost never seen in the syllabus up till 2019, and that is luminous intensity. It does not have a symbol, and however, its units are candela, Candela, and it's expressed as CD. I hope you all caught that. Now, every derived quantity, i.e. quantities that are not the 7 base quantities, they can be derived into base quantities. For example, speed. Speed wasn't there in the list. However, you can define speed using that. So speed is distance divided by time. So the unit of speed is meters per second. These both are SI based quantities. Another one is force. Force is, well, if you remember from your IGCSE days or GCSE, whatever you have done, force, the unit of force is newtons. Some force equal to, and this is force, the unit of force is newtons. And that can be derived into base units. So force, a simple formula for force would be Newton's second law. You may remember, mass times acceleration. mass is kg, and acceleration is meters per second. Meters per second. Sorry, meters per second square. And that is the SI base unit of newtons. Sorry. Okay. And that can be done for all the derived quantities. So let's do another example. This one is quite easy as well. Charge Q. You may also remember from your GCSE days. And the formula for charge is IT. And I is ampere. And T is seconds. So that is the base units of charge. Now we move on to the next part of the lesson, which is scientific notations, which includes both prefix and suffix. So from whatever you have in your syllabus, you only have till 10 to the power 12 and 10 to the power minus 12. So in between these. So I'll give you the prefix, meaning like only the symbol, and I'll give you the value, like what you have to multiply to get its value. And there's a standard. So the first one, like the highest, is tera, which is the symbol T. Terabyte, teragram, which is not usually used, but terabyte you may have heard of before, and its value is 10 to the power 12. Then comes giga, which is 10 to the power 9. Then comes mega, which is 10 to the power 6. And then comes kilo, which is 10 to the power 3. And then comes the normal, so let's say meters, so without any prefixes, that is 10 to the power, well, obviously 0, which is the value itself. Then comes deci, or deci, as some of you may know, which is 10 to the power minus 1. Then comes centi, which is c, 10 to the power minus 2. Then comes milli, which is 10 to the power minus 3. And then comes micro, which is denoted by the symbol mu, 10 to the power minus 6. Nano, which is n, 10 to the power minus 9. And lastly, pico, p, 10 to the power minus 12. So it's from 10 to the power 12 to 10 to the power minus 12. Obviously, there's higher and there's lower, but in your syllabus, this is all you have to know. And that is almost it. We are done with SI base units, except there's one small part left. And you may wonder what is perhaps the use, or why does the SI base units play a role in everything in physics? And that is because SI base units are used to check the homogeneity of an equation. Maybe you have never heard of that term before. Homogeneity means that, or an equation is said to be homogeneous if the base unit of every term in the equation is identical, like on both the left hand side and the right hand side. So let's say a simple formula: speed is equal to distance by time. Distance by time. If this equation are to be homogeneous, then the equation on the left hand side must equal the equation on the right hand side. So V is meters per second equals what's on the right, meters per second. So this equation is homogeneous and therefore correct. Now, this is not to be mistaken, however, because when you're checking for homogeneity, you disregard constants such as pi or any number. So for example, E kinetic energy is equal to half mv square. Half mv square. But when you check the homogeneity of the equation, you do not regard the constant half. So that brings me to my final conclusion that every equation every correct equation is homogeneous. However, not all homogeneous equations are correct. And that is it for the lesson. And I wish you all the best in learning this lesson. It's not that difficult. There's obviously lessons that are a lot harder that comes later on. And thank you for attending class.